This is the second of two videos about shifting the equilibrium. In the first video, we talked about how to find Q, which is the non-equilibrium version of K, and we said that we needed to find directions from Q, our current location, back to K, our equilibrium position, after some sort of a stress happened to the system. So in this video, we're going to talk about the types of stress that can happen in a system that change the concentrations, and then we'll talk about how changing the temperature changes the value for K. Okay, so just to review, when we add stress to the system, according to Le Chatelier's principle, that means we're changing the value for Q, which is our current position. We said our current position was like the crosshair symbol on our GPS. So we change our current position. And so when we talk about stress, stress is something that can be added or removed from either side. So let's look a little bit closer at the different types of stress we can have. So let's include our generic reaction again here. Reactants going to products, where the reactants are the left side and the products are the right side. Okay, so let's start with the obvious ones that we showed on the last page. So one way we can stress the system is by adding reactants. And for each of these different types of stress, let's draw the balance beam to think about which direction the stress affects and which direction the shift goes. Okay, so here's our balance beam with our K in the middle. If we're adding the reactants, that means we're pushing down, we're adding stress to the left side. So the balance beam is going to be lower on the left. Q is going to be on the left side. So if we add reactants by pushing down on the left side, we are going to shift towards the right to reach equilibrium again. Okay, and we also did, if we add products, that was our other picture on the last page. Start with our K in the center. If we add the product, we're pushing down harder on the product side, on the right side. So our Q is going to be on the low end on the product side. So our shift needs to be towards the reactants, towards the left. Okay, so we can add products, we shift left. If we add reactants, the system shifts right. But now what if we have a negative stress? What if we remove something from the system? And you're probably thinking to yourself, we can't remove things from a flask. I don't have a very, very tiny pair of tweezers I can use to reach in and grab something. So removing is more like removing it from solution, reacting it with something or oxidizing it, changing its form. So we'll keep it in quotes. So let's look at what happens to our balance beam if we remove something. So removing a reactant is kind of like making the left reactant side lighter. So that side of the balance beam goes up and the product side goes down. And so if we thought about how Q is always on the heavier side of the balance beam, that means that Q is going to be on this side. So removing a stress from the reactant side is kind of like adding a stress to the right side, the product side. So this time we're going to shift towards the left. We can do the same thing for products. We can remove, quote, products. If we draw our balance beam with K in the center, removing a product means that the right side is getting lighter in the balance beam. So the left side is going to be the heavier side, and that's where our Q is. And we can straighten the balance beam by shifting towards the right. So these situations can be a little tricky thinking about these removing things from the equation. So take a few minutes to think about how this works. Talk yourself through how the balance beam will shift in this case. Okay, so these adding and removing things, these are different ways to change the concentrations of the different substances in your reaction. And if you remember from our chapter on gases, gases and their concentrations are also affected by the volume, because we measure them in pressure instead of concentration, and pressure is affected by volume. So that's another knob we can turn to stress the system. So let's take a look at that. So for gases, when we write our K, we usually write the Kp form, the one with the pressure in it. So pressure is like a way to measure concentration of gases. And something that affects the concentration of gases is the volume. It's one of the first things we learned in this course. All right, so this only applies to gases. Remember, if we change the volume, it doesn't affect the pressure of liquids and solids because they're so dense. So for gases, the volume is going to affect the pressure, and the pressure is related to the equilibrium constant. So we can look at how volume affects pressure by revisiting our old friend PV equals nRT. And we can see that these two variables are inversely proportional. As we increase one of them, the other one will decrease, equal the constant on the other side. So let's take a look at what happens when we change the volume and how that affects the K value. For this example reaction, this time we're going to use actual compounds. We're going to have 2A goes to B with both of them gases. So if I wanted to draw a picture of my box and what my system looks like at equilibrium, it doesn't matter how many particles I draw in here, I always need to draw 2 times as many A particles as B particles. So I'm going to draw 4 particles of A and 2 particles of B. Okay, so now let's add a stress to our system. We're going to stress the system by decreasing the volume. Okay, so we'll decrease the volume by half, roughly. We have the same number of particles in there, so we still have 4 particles of A and 2 particles of B in our compressed picture. Okay, and what happens when you decrease the volume? You increase the pressure. So this system has an increased pressure and it wants to do something. The balance beam has been increased in pressure and wants to shift to relieve it. So the way the system is going to relieve an increase in pressure is to move towards the side with less gas molecules to try and decrease that pressure. So if we look back at this reaction, there's 2 molecules of gas on our left side and 1 on the right side. So the shift for the system is going to be towards the side with the fewer molecules of gas, which is the right side. So it's going to shift and it's going to remove some of those particles of A and turn them into particles of B. And that's how it returns to equilibrium. So we didn't write shift, oh, we wrote it very sloppily. We didn't write shift towards the left or the right in this case because it will depend on your reaction. Sometimes a decrease in volume causes a shift to the left, and sometimes a decrease in volume causes a shift to the right. All we can say for sure is that it's a shift towards the side with the fewer moles of gas. So let's write that down here. So we can stress our system by decreasing the volume. When we decrease the volume, We increase the partial pressures to those gases. And so when we do our shift on the balance beam, we are going to shift toward the side with fewer moles of gas. But to try and relieve some of that extra pressure by decreasing the pressure. Okay, so now let's do the opposite. Let's stress the system by increasing the volume. So we'll try and do something that's a little bit taller here. There we go. We still have 4 particles of A and 2 particles of B after that stress happened. When we increase the volume, we call this expanded. And when we increase the volume and there's much more space for the same number of particles, the volume and the pressure are inversely proportional, so the pressure is going to go down in the system. Let's go ahead and start our list for this one. So if we increase the volume, that is going to decrease the partial pressures in the system. And now there's going to be a shift. Every time you stress the system, there's going to be a shift to relieve the stress. So we would predict that the opposite would happen. Oh, we're going off the screen. There we are. So we'd predict that the opposite would happen. If we decreased the pressure for the stress, the shift would increase the pressure by shifting towards the side with more moles of gas. So we're going to take away some of our B, and we're going to add more of gas A. And we're going to reach equilibrium again. So now there are 7 particles in the container instead of 6. So we've added more gases to fill that space. So that the system will shift toward the side. And W slash means with more moles of gas. Fill that space. So increase in volume, which decreases the pressure, it shifts to increase the pressure by adding more gas. So these are the ways we can stress our system. We can add or remove things by changing the concentration, and we can change the concentration of a gas by increasing or decreasing the volume.